Good afternoon everyone. My name is S.A.ENGINEERING. I am from Assistant Professor. I came from Department of Mechanical Engineering. Today I covered a topic is nothing but free vibration, forced vibration, damped vibration and undamped vibration in single degree of freedom. Okay. In the vibration, this is the GATE syllabus. The section of GATE syllabus for Mechanical Engineering, the oscillation motion of elastic body and the relative forces. It comprising free and forced vibration, damped and undamped vibration in single degree of freedom, and also vibration isolation, the effects of damping, resonance and critical speed, shafts and machine design is also covered in the same syllabus. Okay. The vibration, free vibration, totally it has to be classified by two types. One is free vibration, second one is forced vibration. For example, forced. Free vibration and forced vibration, what does it mean? Is nothing but for example, free vibration it's look like it's a damper. For example, if we have to fix it as a without damper in free vibration, the wave like this. This is the upstairs as well as downstairs, we both are done equal. Okay? So this is the time, this side the distance. The intermediate distance is nothing but the vibration. This is called as what? Free vibration. But always the free vibration curve is look like this. But we have to take it as a forced vibration. It will be ending on this direction. So this is what? Forced vibration. This is nothing but a free vibration. The same T is also here, distance. Okay. For example, the free vibration describes the natural oscillation of a system without external forces. External forces is nothing but suppose I have to take the pen in my hand. Some amount of external forces without added into the particular material. So it looks like a damping in the continuously. Okay, the forced vibration at all, if I added any mass value to that particular pendulum or particular spring system, so on the time only it will be acting on a forced vibration. So forced vibration refers to the oscillation of a system under the influence of external forces. For example, I will tell you one more thing. See, this is the free vibration. One spring has to be induced into that material. After that, this is the mass level. Okay. So, this free vibration considered upon the longitudinal vibration. Longitudinal vibration means upside. This is the downstairs. It's look like the longitudinal movement of the vibration. This is the continuous vibration. Okay. For example, the same thing we have to treat for the forced vibration. It look like this. Suppose if we add it to the mass value m is equal to, for example, only I have to add 250 kg. Clear? So suppose I add it to the particular element means at the time what we have to do? Suppose the weight level will be added to the particular material. At the time what we have to do? It will be induced to the particular type of action movement. Okay? Then the influence of external forces or excitation. Excitation is most important external forces. Differing from free vibration where external forces for absentia. So damped vibration. Totally I have told you already free vibration, forced vibration, damped vibration and then undamped vibration. Then this is the damped vibration. It refers to the oscillatory motion of a system that gradually decreases. Why means over time due to the dissipative effects of damping such as the friction. Friction is the most important thing, or fluid resistance, resulting in a gradual energification energy. Okay. This is the undamped vibration. It refers to an oscillatory motion of a system that persists without any restriction, without any dissipation of energy, maintaining constant amplitude and frequency over timing, typically observed in idealization theoretical scenario. Only the theoretical scenario only we have to read the undamped, as well as practically we don't know about the undamped vibrations. Then this is the single degree of of movement. Okay, already I have conveyed to you, I have to take only single degree of freedom for the free vibration, forced vibration, damped and undamped vibration. Okay, so that time we have to take as a single degree of freedom of a system is one motion should be governed in a single second order differential equation. Okay, first order, second order equation, second order differential equation will be there. So we have to take a single and second order differential equation only. Only two variable positions are velocity are needed to describe the trajectory of the system. Many surfaces, this is the mass. This is the mass. Suppose the mass has to be connected with one damper. This is what? C is nothing but a damper. C is nothing but a damper. This is for what? Spring stiffness. So it's a longitudinal movement. Already I conveyed to you. What is by longitudinal? If one way of movement only, we will treat it as a longitudinal movement. Okay. So this is the time. This is the distance. Okay. So the mass has been movement in the longitudinal, in one way movement. For example, this is the forward motion. Again, it will be retract in the reversible motion. Okay. Two things are only will be there. Why we have to place it as a damper here? This damper has to be controlled the spring movement. Okay. For example, if we have to drive in a vehicle, okay, the same thing. Just a minute. So this is the vehicle wheel. So this is the damper. Just be connected in the wheel. For example, if a vehicle has to be passing on the road, okay, at the time the damper has to be placed to the wheel. Okay, why means it has to be spring. The spring has to be placed each and every upward and downward motion continuously. At the time we have to place as a place as a damper in this place. The damper has to be avoid the spring movement. Okay, so then this is nothing but a same wheel. Right now I have to utilize a damper. Okay, so this is for forced vibration. This is for free vibration. This is for forced vibration. Okay, are you understand? Then free vibration, actually I told you the longitudinal movement we have to see. Then other two things is nothing but a transverse and a torsional. What is by transverse? Suppose if we have to rotate any pendulum or any X models material, it will be rotated completely clockwise or anti-clockwise. That is called as transverse. What is by torsional? Suppose we have to take as a pen with a cap as well as rotating in opposite direction. That is nothing but a torsional. If torsion has to be increases, at the time friction is also reached the highest level. Okay. So these three types of vibration will be considered in free vibration. First thing is nothing but longitudinal. Second thing is nothing but transverse. Third one is nothing but what? Torsional vibration. Okay. Sorry. Actually, I have taken only 4 types of problems comes under free vibration, forced vibration, damped and undamped vibration in single degree of freedom. Okay. So right now, the concentrated mass M is attached at the center of rod of length is nothing but a 2L. Length is 2L. As the shown in figure, a rod is kept in horizontal equilibrium position by a spring of stiffness K for every small amplitude of vibration. Neglecting the weights of the rod and spring, the undamped natural frequency of the system is. Here the diagram has to be given. 4 values has to be given. A is root of K by M, B is root of 2K by M, C is root K by 2M, D is root of 4K by M. Okay, right now we have to solve the problem. Okay. So this is the diagram. Actually, this is the overall length. 2L value has to be given in the question. So that's the value. So this is the theta. The theta has to be measured for smallest value. We have to compare the angle value. Then the starting point is fixed. It is a fixed one. The fixed value is 0. Okay. This is the x. This is x. This is the kx. Okay. From the above figure, we have to frame as a equation. X is equal to 2L sin theta is equal to 2L theta. Why here sin theta has to be changed as a theta means is very small value. So small value we have to take sin theta approximately equal to theta. Mass moment of inertia also we have to identify. The mass moment of value is nothing but I is equal to m into L square. So also internal forces acting on the system. So governing equation of motion we have to convert. Okay, we have to follow the Newton's law of motion. Then finally, this is the equation for the one I theta is equal to I theta plus kx into 2L equal to 0, or otherwise one more equation should be there, m into L square theta plus k 2L theta into 2L. Then finally we have to take the equation like that. The next thing is nothing but comparing with the general equation. Why we have to compare the general equation? Then only we have to know the omega n square value. After that we have to got the omega n square value. We have to take the square root. Then finally identify the omega n value. Okay. So finally we have to take theta plus omega n square equal to 0. We have omega n square is equal to 4k divided by m. Okay. So finally I have to take as a square root here. Omega n is equal to root of 4k by m. This is the solution. So we have to go to the previous slide. Then this equation is which one we have to select. Okay. Yeah. D is right. Finally D is right. The value is nothing but root of 4k by m. Okay. Then we have to look at the second problem. Okay. The second problem is a disk of mass m is attached to a spring of stiffness k. Okay. Then as shown in the figure, a disk rolls without slipping because it will be passing in the two unarrested area. It's arrested area. This is also arrested area. Two unsurfaced arrested area are there. This side is not arrested. That side is also not arrested. Top side as well as right side is not arrested. Okay. Downstairs as well as left side only it will be arrested. Then only one spring has to be introduced to attach with the disc. Okay. Not even a damper. So at that time this problem will be considered as a free vibration as well as forced vibration problem. Okay. So four options has to be given. A 1 by 2 pi root of k by m. B is 1 by 2 by root of 2k by m. C is 1 by 2 pi root of 2k by 3m. Then finally D1 is 1 by 2 pi root of 3k by 2m. Right now we have to see the solution. Okay. Right. Right now the mass has to be connected with the spring constant. This direction is the x direction. This is x direction. Then we have to take the disc separately here. I have to draw the complete nomenclature of the diagram. So this is for angle R, this is the theta, this is the x direction. Okay. Then theta is equal to x by r. So x is equal to r theta. Okay. This is the equation number 1. Okay. Then second thing is nothing but T. What is my T? Total energy is equal to kinetic energy due to translatory motion plus kinetic energy due to rotatory motion plus potential energy of spring. Here T is nothing but the total energy, K is nothing but the kinetic energy, P is nothing but the potential energy of spring. Okay. Then total energy of the system is equal to, what is the formula for Ke due to translatory motion of mx square, then due to rotatory motion of I into theta square, then finally P of the spring of into K x square. What is the value of x? Already we have to frame what is the value of x? X is equal to r into theta. So we have to substitute the x value in the given equation. Okay, of mx square. So x value is r theta. So r square theta square. Okay, we have to substitute it here. Then plus 1 by 2 I naught square. There is no x here. Plus 1 by 2 k r square theta square. Here also x is there. So we have to substitute r square as well as theta square. Okay. Then finally we have to multiply with the I value also, because already I have to convey to you what is the value of mass moment of inertia, m into r square by 2. So at the time we have to multiply with other thing. We have to multiply with the other things. This is equal to constant. So on differential above equation, with respect to t, we get 3 by 4 m r square into 2 theta. That is a theta square. Okay, theta into theta square, plus 1 by 2 k r square. 2 theta into theta is equal to 0 because of the constant value. Okay, then finally we have to know the omega n square value. What is the omega n square value? Is equal to 2k by 2k divided by 3m. The same value has to be present in this equation. Then we have to take it as a square root of omega n. What is the value of omega n? Is equal to 2k divided by 3m. Then the natural frequency of the vibration of the system is Fn is equal to omega n divided by 2 pi is equal to 1 by 2 pi root of 2k divided by 3m. So finally we got the solution for the natural frequency. 1 by 2 pi equal to root of 2k by 3m. Okay. This is the solution. So now we have to check which one it is. Okay. 1 by 2 pi 2k by m. This is the B is the right answer. B is the right answer. Okay. Then next problem is a mass m is attached to a spring is subjected to a harmonic force. So in this place we have to utilize the harmonic force. Harmonic force as shown in the figure already. The amplitude of forced vibration is observed to be 50 mm. The value of m in kg. Already m value in kg. It has been given. Okay. So k is equal to 3000 Newton meters 1 meter power minus 1. Then m value already given. What is the value of m? This only we have to identify from the given question. Then f of t, force into time. That is nothing but 100 cos 100 t Newton. Okay, 100 cos 100 t Newton. So 4 value has been given. First value is A is nothing but 0.1, B is 1.0, C is 0.3, then D is 0.5. So finally we have to identify which value is right. Okay. Okay. This is the given diagram. The given diagram has to be replaced here. The K value is 3000 Newton per meter. Then C is nothing but damper. There is no damper has to be fixed with the given question. So C value is equal to 0. Okay, A is equal to 50 mm, then Ft is equal to 100 cos 100 t Newton. Okay, then omega t is equal to 100 t. So what is the value of omega? 100. Okay, it is the forced vibratory system. It's a forced vibratory system. So this is comes under forced vibration. Okay, so this is the alternative formula because it is the easiest thing we have to complete a problem. So that's why I select this problem. Okay, alternative problem is also, formula is also there, but we have to taking n number of r's. Okay, so that's only I am taking a simple equation. A is equal to f naught divided by root of k minus m into omega square plus c into omega square. Already we have to know what is the value of f, what is the value of f naught, what is the value of a, what is the value of k. Each and everything we have to know already. So we have to substitute the entire value in the given equation. Then a is equal to f naught divided by k minus m omega square. So finally we have to take it. Clear? The square root will be going on. Then finally a is equal to f naught divided by k minus m into omega square. So k minus m omega, so we have to do the cross multiplication here. So then only we have to identify the m value. Okay. So k minus m omega square is equal to f naught divided by a. So what is the value of k? 3000 minus m. M value we don't know. We have to identify the m value. Okay. Then omega square value is 100 square is equal to f naught value is 100. A value is 50 into 10 power minus 3. So we have to substitute n number of values in the given equation. Then finally we have to conclude the value of m is nothing but m is equal to 0.1 kg. M is equal to 0.1 kg. So right now the 0.1 kg is which option? So we have to look at it here. Yeah, first one is right. First one is right. So 0.1 kg is right. Already have been given m in kg. So 0.1 kg. Okay. Right now we have to look at the final problem. Okay. This is the most easiest problem. The natural frequency of the spring. The natural frequency of the spring mass system shown in the figure is closest to. So m value already given 1.4 kg, k1, k2. It's a spring constant. That both of the spring has to be placed in series. Okay. Then A option is 8 Hertz, B option is 10 Hertz, C option is 12 Hertz, D option is 14 Hertz. Okay. Then m is equal to 1.4 kg, k1 is equal to 4000 Newton per meter, k2 is equal to 1600 Newton per meter. It has to be given. In the given system, k1 and k2 are parallel combination. K1 and k2 are parallel combination. So natural frequency of the spring mass system is being given by K equivalent. First of all, we just identified what is the value of K equivalent? K1 plus K2. So at the day, what is the value of K1? 4000 plus what is the value of K2? 1600. And finally 5600 Newton per meter. This is the K equivalent. Okay. So K equivalent value is 5600 Newton per meter. Then natural frequency values for what? F1 is equal to 1 by 2 pi root of 5600. That is K equivalent divided by 1.4. Okay. That is nothing but M. F1 is equal to 1 by 2 pi root of K equivalent divided by M. Okay. So the value has to be substituted in the here. F is equal to 1 by 2 pi root of K equivalent divided by M is equal to 1 by 2 pi square root of 5600 for K equal value. 1.4 is nothing but the M value. Already it has been given in this place. 1.4 kg. Okay, so we have to substitute the 1.4 is here. Then finally, what is the value I got it? 10.07 Hertz, approximately 10 Hertz. So finally, we have to conclude the value is nothing but 10 Hertz. Okay, so right now, which option is right? We have to see. Okay. Okay, 10 Hertz.